Following on from these incredible speeches so far, we've learned about data and how that represents the future going forward. What I'm going to talk about is the compute that goes alongside that data, the new type of compute, what we could call compute 2.0, that supports this data-enabled world. So just to talk a little bit first about GraphCore and who we are and some of these images that you're going to see inside my slides here. These are created by the software that goes together with the processor that we're building, what we call an IPU, another term to be put into the lexicon, an intelligence processing unit, which really creates this new wave for supporting machine intelligence. What we're really building is a processor that will allow you to develop, allow the innovators to develop the next generation in machine intelligence. Many of those people are working with us. Some have even invested in our company. They're working with us so closely. And really, the way to think about this is for 70 years, we've told computers what to do step by step in a program. We've literally programmed the devices, they've run algorithms, and they've come up with very specific solutions to answers. And algorithms can help us solve certain problems, but there are many problems, I would argue most of the problems that we need to solve are intractable to an algorithm. These problems are too complex, either because it'll take you too long to compute, or it'll take you too much data to really be able to come up with the answer. And really what we need to be able to do is to come up with solutions to these problems in a very different way. And that's really what machine intelligence allows us to do. It allows us to learn from the data to be able to come up with solutions to these very complex problems. It's what we do as humans naturally. We naturally deal with very imprecise knowledge, and we learn and we manage to come up with sensible answers. And that really defines intelligence. Some people say, what is intelligence? Is it something we can really write down and describe? And I think it's really very simple. Intelligence is the capacity for decision making based on imperfect knowledge, because we never have enough information. We never know the precise answers. And then we adapt based on our experience. And as we get older, we get better. As children learn, they make better decisions. So that's really what we should think about as intelligence. And it's what is needed to converse. It's what's needed to drive a car. It's what we do, as Jung was describing, him driving down the road. Those are the decisions he's making. He's overlaying his need for speed on top of that. But what we're really here thinking about is we've learned how to drive. We're making decisions. We don't know all the answers. We don't know quite what's around the corner. And we're coming up and we've adapted based on the experience of driving down this road before and maybe knowing there's a junction just around that corner and we can know what to do about that. But also it opens up massive opportunities. Drug discovery, for example, huge problem. Where even within the space should we explore? Where should we do experiments? How do we make drug deliveries such that we actually can get the drug exactly to the disease and not create side effects? All of these, are massive opportunities for us using this new technology. And really, how does this all work? And how is it working today? Why suddenly are we talking about machine learning? How has it suddenly all come together in what feels like a absolute shortest time ever? And really, what's happened is we now have access to all this data. Much of that data has some labels. And what we can do is we can use that data by combining that with models, building it into machine learning models to capture that data as a digest. It's a probabilistic model. It represents the knowledge that we're capturing from the data. But what we need is hardware that allows us to process on these models, because this data is now represented in a very high dimensional structure. We're capturing the salient features from the data and the corresponding relationship between those, the probabilistic relationship between those. So the compute that we require is doing some very fundamental things here. And it's interesting, people talk in machine learning about training. they talk about inference, but really they're the same thing. They're both inference tasks. What we're doing in training and learning is we're learning from the data. We're learning what are the important parameters within the data, the features within that data that we can really need and understand. At the moment, we're building the structure of these models. We're actually hand coding those. We're still programming those models or the structure of the models. But going forward, even as part of the learning process, we'll actually infer what the right structure is for these models. And that will become part of the learning process. And then having built the model that captures the data into some form of knowledge, it represents the knowledge associated with this data, we can then apply new inputs and create outputs from it. So if I build a knowledge model or even an ensemble of models that go to make up a driverless car, I can then put new camera data into that, and it will come up with sensible actions and decisions to be able to drive that car safely down the road. And what it may need to do is it comes across a new situation, it will need to come up with sensible answers in that new situation, and maybe it won't get it quite right, but maybe it will learn from that experience and it will feed back in. So even at the edge, we're going to have devices that learn. And we were talking here just in the last speech about this idea that at the edge, we're going to be collecting so much data, we can't send it all back to the core. We need to extract from that data what is the interesting salient features, what is the knowledge that I've learned from this data, and then we're sending back submodels to the core, which then can get worked on into higher level of intelligence. So what's the compute at the heart of this inference engine, as we call it? Well, it's a completely new workload. It's unlike anything we've seen in computing so far. In this world of small data, as Shankar called it, we worked on very dense sets of data where all of the definitions were known. We were applying algorithms that would come up with precise answers to these problems. But here, we're dealing with abstract functions. We're dealing with probabilities. We can expose massive parallelism. We can expose all these features, all these parameters. There are millions of parameters that we're exposing. There are hundreds of millions of connections potentially between these parameters, or possible connections, some of which will be relevant, many of which won't be. So we have huge parallelism within these problems, which we can now use on highly parallel processors. The data structures are fundamentally sparse. Not all of these parameters to connect to everything else. So the data is fundamentally sparse. And the problems are very high dimensional. And we're mapping those into memory structures. And memory structures are very low dimensional. And when you do that in a high dimensional space, I have many neighbors, other pieces of data that it relates to. And when I put it into a memory, I can only have two neighbors, right? Because I've got a linear addressed memory. So the rest of the data is spread out. All the other connections are spread out across the data. So I need a processor that can go and capture the data, bring it together to do the compute, scatter it back to where it needs to be done. And the compute that I'm doing is low precision, because it's the ensemble of all these small calculations that go together to make the highly precise answer that I'm looking for as the output from my model. The model parameters have lots of reuse, convolutions, recurrence, so I can reuse structures within the element. So it's not like I need separate processors for every parameter. I can reuse the processes in very clever ways. And they're fundamentally mathematical graphs. And they're static, just like in our brain. You don't rewire the neurons every time you start a new task. The neurons are fixed. It's a static graph that we're working with. And within that static graph, we can use that to make the tools that will allow us to map these complex problems to these highly complex processors. And the last point here, entropy, what does that really mean? Well, that means noise. These are noisy problems. We don't know the precise answers, and sometimes actually injecting some noise will help us to come up with a decision. I'm standing in the middle of the road, a car is coming towards me, I could equally go to the left, I could go to the right, I could be struck with paralysis, not knowing what to decide. And actually the only way to solve that problem is you throw a little bit of noise in and force me to go left or right, because both are perfectly good answers, right? So noise and the ability to generate noise within this compute structure becomes very important as well. So what potentially is going to limit the performance of these new hardware machines? Well, the compute. We need massive amounts of compute to train these models. It requires huge amounts of computation. It's low precision, but we need very high rates of arithmetic to be able to be achieved. We need massive memory bandwidth because we're dealing with lots of really incredibly complex data here, and we need massive bandwidth to be able to get this data to the compute. But the problem is it's not just about having massive bandwidth in one direction. I want massive bandwidth in lots of directions. I need to be able to capture data from lots of different places, bring them to the compute as it's required, and scatter back to where it's needed. So it's about address generation as well. And finally, we need this ability to work with random numbers, stochastic rounding on my arithmetic, generations of entropy within the compute structure so that I can support these next generations of machine learning structures. And there's one final point, and I think this was highlighted in Pradeep's presentation as well. Connectivity is absolutely critical here. As I put more and more processor cores down onto my silicon, as I put thousands of processor cores down, which is what we're doing at GraphCore, it's not putting the thousands of processors down that's difficult. It's how do I connect them together? How do I get data to them? How do I get them to communicate? How do I get them to cooperate? The interconnect between those is absolutely critical. And many, many years ago, there was a research scientist at IBM Research, and he looked at this problem in chip design in terms of how do I understand how much interconnect I need versus how much logic I have. This guy called Rentz, he came up with this rule, basically. There's a power law scaling. As I put more logic down, I need a power law more of interconnect. And incredibly, that same rule applies in so many different places, including in our brain. As we look at sections of the brain, as you put more neurons down, you need more connections to that. So we've got 100 billion neurons in our brain, as Jung pointed out to us. But we've got orders of magnitude more connections between those neurons in the brain. So the connection grows, the number of connections grows. So building the interconnect in these chips and the ways that we manage the software to these chips is really the critical problem to solve. And that's what we've been doing in GraphCore, understanding the workload and how we build the interconnect and the software that can drive this. And what you end up with is a new type of processor, something we call the IPU, the Intelligence Processor Unit. It's the logical name for this new type of processor, and it's fundamentally different. It's fundamentally working on these graph-type structures. It will work on any type of design, not just neural networks, but other kinds of machine learning tasks that people are looking at. It will allow us to combine machine learning concepts together in ways that are not possible. It will allow us to work on recurrent structures that imply memory within the designs. It will allow us to support the next generation of machine learning topics. We've created a very simple software environment. We've worked with the leading framework vendors. We're partnering very closely on TensorFlow to have a completely seamless interface. So we're not asking people to learn a new language. We're not asking people to learn some new concepts. Right in TensorFlow, seamlessly will work down into the hardware, which will deliver as simple units, PCI cards, or other modules which can plug into existing servers and into modules that we can put inside autonomous cars, and smaller modules that eventually we can put right at the edge of the network to deliver this new type of compute into all the applications that need intelligence added. Just to give you a brief hint of the performance potential that we have, we'll be launching some products next year. If you take the latest GPUs, the ones that you can't even buy today that are coming out next year, you take the same power consumption, the same form factor. On the workloads that people are doing today, the feed-forward convolutional networks, the kind of networks that people are working on today and are being deployed, we're about 10 times better. Obviously, those were designed because GPUs were the only thing around. Just like when we started making cars, we kind of took the horse away and we bolted an engine on and we kind of created a horseless carriage. It was kind of what we could do when the cars first came along. But very quickly, we worked out what was the right way to build cars, and they now look very different from those early days. And IPU is the architecture that will support this revolution in data, this revolution in artificial intelligence, this revolution in compute 2.0. And as we look at workloads that people are working on today for recurrent structures, long short-term memories, the kind of things we need to make much more complex machine learning systems, our IPU at that point is 100 times the performance. Same power, same size, same cost, 100 times the performance. And not only that, it reduces the latency by 10 times as well. So when we're driving our cars and we need to make those decisions, we need to make those decisions quickly. We're in the middle of the junction, something's happened, we need to work out what the answer is quickly. And the latency is reduced by a factor of 10 as well. So all of these are fundamental breakthroughs in the compute structure and the delivery of this type. So that's why we claim our IPU, our intelligence processing unit, lets innovators create the next generation of machine intelligence. It will provide a massive breakthrough in this incredibly important area. And we walk in the footsteps of giants. This isn't a new idea. Alan Turing talked about this 70 years ago. We need machines that can learn from experience. We're now just starting to build them. Thank you very much.